Hey, Jason, can you hear me now?
Yeah, you
This should be a little better. Yeah, no, I left and I came back, but I also connected to my hotspot at home because I don't know, there's something going on. I'm not sure if it's Cerrito's internet or my internet or what, but I think we should be better now. Were we okay with number 6? We were going on to number 7, I think, right?
Yeah.
And you started doing number 7 or not yet?
Not yet.
Not yet. Okay, that's fine. So let me just get 4.1. Let me get the homework. There we are. Whoops. I think okay. 4.1 sample spaces probably. There we are. Okay. Okay. So number 7 says, if a die is rolled one at a time, so a single die, find these probabilities. So let's think about our sample space, okay? So a sample, what outcomes can I get for a single die?
1 to 6.
Right, 1 to 6, right? So there are 6 outcomes. When you're looking for a probability, the way that we find it, one of the ways that we find it, because we're going to learn a lot of rules in this chapter, but one of the ways that we look at probability is we look at it and we say, well, okay, I'm looking at my probability and I'm going to say that it's equal to the probability of some event is equal to the number of ways to have that event divided by the number of outcomes in the sample space. So the number of ways to get the event divided by the number of outcomes in the sample space. So in this case, we know that there are 6 outcomes in our, we know there are 6 outcomes in our sample space. How many of them are we interested in?
2.
Okay, be careful. That's a common here. The question doesn't say, it says getting a 2, getting a 2. So a 2 is actually 1 outcome. It means that we're rolling the number 2. Remember, we can either roll a 1, we can either roll 1, 2, 3, 4, 5, or 6. Okay, we're interested in just this outcome, just rolling a 2. Okay, that's 1 outcome out of 6.
This was from similar to, I would think it was 3.4's notes.
Kind of, yeah. I mean, you're gonna see some overlap, especially in the videos that go up in the next couple of days between 4.1 and 4.2, because there's a lot of concepts that overlap in these 2 sections. But this sample space, this isn't, okay, this doesn't happen to be the 5-number summary. It just so happens that there's 6 outcomes in the sample space. This is my, whoops, this is my sample space here. So, and usually we show sample spaces with what we call curly braces, like this. This is my sample space, okay? So there's 1 out of 6. And usually what we do when we do this is we go ahead and we write the fraction, and then we show the decimal on the percentage, which she usually does. So what we're going to do here is I'm going to bring up the decimal. Well, I'll do the fraction first. Let me make sure that I'm showing the calculator here. So my fraction here, oops. I said that and then I didn't do it. Okay, there we go. My fraction here is 1. I was doing some earlier today. This is 1 out of 6. So my decimal is 0.16666 repeating. And if I multiply this by 100, I'll get my percentage. So I have 16.67 if I round it, percent. So we would write this as 0.1667, and this would be 16.67 or 16.7%, depending on how many decimal places she wants. She usually specifies 3 or 4 decimal places, depending on the context of the problem she's doing. But that is for the first one, the probability. So our event here was, my event was rolling a 2. And so the probability of 2, the notation takes a while to get the hang of. The probability of rolling a 2 is equal to 1 out of 6, which is equal to that. Okay. What do you think about the next one, which is, let's see what it says. The next one is asking us for the probability of getting a number greater than 6. Getting a number greater than 6. So
the possibility of getting a number greater than 6?
Mm-hmm. Would be what? Is it possible to do that?
No.
No. When an event is not possible, what is the probability?
0% chance.
Yeah, so 0, right? That's all you do there. Because this event, this is an impossible event. Yeah, you can't get a number greater than 6 if you're only rolling a single die, okay? All right, let's do the next one. What does the next one say? The next one says, getting an odd number. An odd number. So let's look. What is the probability of getting an odd number?
On a single die?
Right.
I would say there's 3 chances, or
Right. You're on the right track. 3 out of how many?
3 out of 6.
3 out of 6. Remember, probability is a fraction. So yeah, so there's 3 outcomes that match it. So here, the probability of an odd number, right, is equal to, remember, the number of ways to get the event. Now, what ways are there to get the event? There's, as you said, there's 3 chances. What are they? 1,
3, and 5.
3, or 5. So there's 3 chances, right?
Mm-hmm.
So there's 3 chances for the top, the number of ways to have the event, over the total number of events in the sample, which is 6, right? So we have a 3 out of 6 probability. Huh? And that would be
5.
1 out of 2, or if I reduce it, it's 1 out of 2.
Mm-hmm.
And what percent is that? Do you know what percent that is? Do you know what the decimal is for this?
0.5.
Right, this is 0.5, right? And so that's equal to 50%, right? 50% chance. Okay, now what if we said, what is the probability of even or odd number?
I'll be like, I don't know.
Well, if it's even or odd, it has to fit either group. So how about number 1? Is that even or odd?
Odd.
Odd, so it fits the odd group. That's okay. We can deal with that. Number 2 is
even.
Even, so that fits the even group. Number 3 is another odd, so it goes with the odd group. So every number in here, right, fits one of these 2 groups, doesn't it?
Yep.
Now, what you're going to see in the next section, you don't have to do it here, but what you can do is break this apart if you want so you can see it better. When you have an or, you're doing addition. So here you have the probability of being even plus the probability of being odd. Okay, but the fact of the matter is that any of these numbers correspond to that. So here we're going to have probability of even or odd. And this will make more sense when you get into 4.2. But this becomes, so how many even numbers do we have?
We have 3.
3. So that would be 3 out of 6, right? 3 out of 6. How many odd numbers do we have?
Also 3.
3 also, right? You see where this is going? Well, if they're either even or odd, this gives us 6 out of 6, which is 1, right? And that means, right, this means that we have This is 100% now, right? And this is what we call, this is an absolutely certain event. You can only roll an even or an odd number. No matter how many dice you have, you can only roll an even or an odd number. So this is an absolutely certain event. And I think she just wanted to give you an example so you could see what those events look like. So a number greater than 6 is impossible, but a number that's even or odd, that's the only thing you can have, is either an even or an odd event. Okay?
Yep.
So that's it for number 7. Let's go on to the next one, which I think is, yeah, this is our dice situation. So 2 dice are rolled at one time. We haven't gone over this yet. This was actually going to be my next my next sample here. So we're going to go to our sample space for 2 dice. Let me see if I can find it. Now, this is 2 dice instead of 1. Okay, so let me go to my 4.1 here. Let me go to the sample space for 2 dice, because she does give it to you. It is on slide number, let's see. It is on slide number 8. Okay. It's on slide number 8. There's your sample space for 2 dice. So let me make sure I'm sharing the screen, because I'm not sure I am. No, I'm not. Let me also make sure that it actually appears before I, okay, let me just see if I can put this up here. Okay, I think I can share it from here. Let's see. There it is. All right, so here's your sample space for 2 dice, okay? Couple of things to point out here. The numbers on the first die, 1 through 6, the numbers on the second die, 1 through 6. There are a total of 36 possible outcomes here. Okay, because, and part of the reason is that these numbers can repeat in a different order. So for example, 2-1 is a different outcome right here than 1-2. Okay, 2-1 means you rolled 2 on the first die, 1 on the second. And 1-2 means you rolled 1 on the first die, 2 on the second. So there's a total of 36 outcomes. Now, the sums can go from, the smallest sum we have is what?
1.
No. That's the smallest single number, but what is the smallest sum if I add the numbers together?
Oh, 2.
Yeah, so be aware that on 2 dice, because we do a lot of problems with 2 dice, although she didn't give you too many here. A sample space for 2 dice has 36 outcomes. Okay, order matters. Okay, So 2, 1, and 1, 2 are not the same. And also the smallest sum is 2. And the largest sum is 12, okay? 6 and 6 is 12. So just a couple of things to be aware of, okay? So we're gonna be looking at some probabilities in just a minute here. So while I'm here, let me go to the homework and let's look. And I'm not looking at the right, okay. So this is, okay. So here's our first question. If 2 dice, this is number 8, if 2 dice are rolled one at a time, find the probability of getting these results. A sum of 9. A sum of 9. So let's go back and look for a sum of 9 on 2 dice. So let's look here. Let's find our sums of 9. Okay. So we're looking for probability of a sum of 9. So what do you see on your screen? How many ways are there to get a sum of 9?
1, 2, 3.
I see one more. I'll show you.
4.
Sum of 9 right here. Here's 6, 3.
Yes. Then there's 4 and 5, or 5 and 4.
Right.
And also 3 and 6.
Right. And I'll show you something cool about the sums. Watch this. So let me show you this, because this will help you when you're counting it. Let me spotlight this so that it will show up. So here, 2 is not that hard. The only way to get 2 is 1 plus 1, right?
Mm-hmm.
The next sum, look at what happens when you drop a row and go up. 1, 2, 2, 1. That's the ways to get a sum of 3. See that?
Mm-hmm.
Look at the 4s. 3, 1, 2, 2, 1, 3. They're all on diagonals.
Mm-hmm.
All the sums are on diagonals. So 4, 1, 3, 5, 2, 3, 1, 4. They're all, and the doubles, which is a question that's coming, are all on the middle diagonal going this way, which is kind of cool. So anyway, sum of 9, we said there were 4 of those, which you can see boxed in purple on the screen. So here,
there's
this
4.
is going to give me 4, and out of how many total?
Out of 36.
Right, 4 out of 36. So now I have to do my little mathematics, but this is my original answer, 4 out of 36. So now I'm going to do a little bit of cleaning up here. 4 out of 36, and I'm going to reduce this fraction and then convert it. So I'm going to say,
as in converted, as in divided by 2 on both sides.
Yeah, you can actually you can divide by 2 twice, because 36 is divisible by 4, but yeah. So this is gonna be, let me put it on the whiteboard so that we can see it better, okay? So we're talking here about a sum of This is the probability of a sum of 9 on 2 dice. Just to help us, this we said was 4 out of 36, which reduces to, if I divide everything by 4, this reduces to 1 out of 9, right? And then I can get my, now, if you're not sure, remember your calculator is your friend. Sometimes in this class, he may not seem like it, but it is. So this is 4 out of 36. And if you go math, convert to frac, it will give you the reduced fraction, which is kind of cool. There's your fraction.
I also got that. I also got 11.1.
Okay. And if you want to go to decimal from there, you can go down 1 and convert to decimal. Beautiful. 11.1 is your percent. 0.1111 is your decimal. Good job. Nice. So the hardest part of these is not doing the math. Hardest part is understanding the sample spaces. That's the new concept, is understanding how the sample spaces work. Okay. Most of the problems that she gives you from this section will be, there's going to be a lot of problems that are similar to these examples. So let's take a look at the next one. What do you think about B, a sum of 7 or 11? A sum of 7 or 11. Let me put the sample space up for you.
Sum of 7 or 11.
So here we're doing the probability of 7 or 11. Now remember, or means we're gonna add. So I would suggest counting all the ways to get 7 first.
I got 5.
And then all the
7.
ways to get 11 next. That would, it just makes the math easier. So for the ways to get 7, there are actually 6 of those. Let me show you why.
Oh yeah, I miscounted.
Okay, that's all right. 1 here, 2, 3, 4, 5, 6. So there are 7 of those, 6 of those. That's easy to mess up on. There are 6 of those. So we have 6 out of 36. How many 11s are there? How many ways to get 11?
Okay. 6 plus 5.
Yeah, so let's do.
And 5 and 6.
Okay. 6 and 5, 5 and 6. There's only 2, right?
Yep.
There's only this little diagonal down here. So now we're going to add those up, right? So we have, there's 2 out of 36 here. If I add 6 out of 36 and 2 out of 36 together, how much does that give me?
8 out of 36.
8 out of 36. And if you need help to reduce the fraction,
They're both divisible by 4, are they?
they are both divisible by 4. So this should be 2 out of 9. Very good. And then you can get the decimal and the percent by yourself. Very good job. 2 out of 9, good. Okay.
Mm-hmm.
All right. How about, I think the last one is asking for doubles, isn't it? Let's see. I think the last one, yeah. 8C, it says, is doubles. If 2 dice are rolled one at a time, find the probability of getting doubles. Doubles means the same number on both dice at once.
Yep.
So let's go back to our friend. Here's our sample space, right? What are we looking at when we're looking at doubles now?
We get 6 out of 36.
Right, we're looking at these here. 1, 1.
They're like all across.
Mm-hmm. That's right, the entire diagonal. So once you learn it, it's not that hard to find them. Once you see, there's a lot of nice patterns, and that's probably why they got studied first, because it was interesting to study all the patterns that were there. These are all the doubles. And so we would say this, we would say the probability of doubles, okay, can I type today, is 6 out of 36. And we know that reduces to 1 out of 6, which we can then get the decimal and the percent for, which I'll leave you to do on your own. But that's how that works. So that's how that
16.7.
yeah. Very good. Good job. Now the next thing she wants you to practice on is, I believe we're doing cards next. How familiar are you with the standard deck of cards, Jason?
Not really, because I never play any card games. So like no poker, no goldfish,
no
any solitaire.
Of those. Okay. No, that's why I'm asking, because I have learned to ask and not assume. Because believe me, you're not the only one. In fact, people who are already familiar with it are usually in the minority in this class, which is unfortunate because there's a lot of assumptions behind it. This is our standard deck, okay? And I did record this morning, so if you want to go back and watch this at some point, you can. Because there'll be more card probabilities coming up in the upcoming sections, but I do give a little bit of a an overview on that too. So so now you can either rewatch this or you can watch that. So normally when you have a card probability like this, they'll talk about either an ordinary deck or a standard deck. Ordinary and standard are the same thing. That means that you're dealing with 52 cards, which are the 52 cards that you're seeing on the screen right now. A regular deck, if you go and you buy a deck, you go to Dollar Tree, wherever you go, you buy a deck of cards, there'll be 54 cards in it because they have 2 cards that they call jokers that are wild cards. So what they've done is remove the jokers and we're dealing with 52 cards, okay? Now, you probably heard some of this terminology before. Some of it may not be familiar to you. We have 4 types of cards in the deck. We have clubs. Clubs look like 3-leaf clovers that are black.
I know what they all look like. So spades, hearts, diamonds.
Okay, so you know what they all look like. And yes. Do you know what face cards mean?
Those are jacks.
Could be jacks. This is a queen. This is a king. They're all considered face cards, okay? Face cards have people's faces on them, okay? Even though in a lot of card probabilities, we talk about an ace, which is the ones. We talk about an ace being low or an ace being high. We don't really deal with that too much in this class. She doesn't really emphasize that too much. So normally aces are low for us, which means they're ones, unless we tell you, okay? And also, just because I know people have asked in the past, if your face cards, depending on the kind of deck you're looking at, if your face cards have multiple colors in them, like this has yellow and red in the queen, and it's predominant color. So spades and clubs are always considered black. No matter what other colors you may see, spades and clubs are black suits, and hearts and diamonds are red suits. Okay. Each type of card that you read prior is called a suit. Okay. Each denomination of card, ace, 2, 3, and so on, is called a rank. Okay, so suits, there are 4 of those. Ranks, there are 13 of those. So there are 4 suits, there are 13 ranks of cards. Okay. Any questions about this?
Nope. I know all the cards.
Cool. All right. So let's go and see what they're going to ask us for. So here's our first probability. We want to find the probability of getting, we're drawing 1 card. Okay. That's not going to be, sometimes in other sections, we're going to draw more than 1, but right now we're drawing 1 card. What's the probability of getting a queen from that?
Let's go to let me just go to the chart.
Here's your chart.
12.
Be careful. How many queens are there?
Oh, 4.
4 out of how many?
52.
Right. Remember that a probability is a fraction. Okay. So 4 is the number of queens, but the probability of a queen is 4 out of 52. Okay. So this is, oops, we're going to look for, and I did make a video this morning. It's probably going to be, it's rendering as we speak. So it'll be up after lunch where I did this problem again. So you'll be able to watch it. But the probability of a queen, oops. The probability of a queen is 4 out of 52 or 1 out of 13. 1 out of 13. Okay, let's go on to the next question. The next question says, what is the probability of a club? A club. Well, let's look at the clubs. How many clubs do we have?
We have 10.
No. Face cards count.
Oh, 13.
13 clubs. Yeah, so even if they're face cards and they're a suit, they still count as part of that suit. So there's 13 clubs out of how many cards?
13 out of 52.
52, right. So now we have the probability. If I want the probability of clubs, this is going to be 13 out of 52, which is
1 out of 4.
1 out of 4, and that's 25%, right? 0.25. And that's equal to 25%. Good job. What about if I asked you to give me, oops, let's move this over. Okay. What about if I said, whatever's next, hold on. Okay. What is the probability of getting a queen of clubs? Queen of clubs. So here, how many cards are the queen of clubs?
How many cards are the queen? Just one.
Yeah, there's only one queen of clubs, right?
Mm-hmm.
So it's 1 out of 52 is our probability, right? Because there's only one of her. So here, this is going to be the probability of
Queen of clubs.
queen of club, right? And that's going to give me, it's going to equal
113.
1, careful, 1 out of 52.
Oh.
Right? Because it's out of the whole group, right? 1 out of 52. There's one queen of clubs and she's 52 cards, right? All right, let's go on to the next one, which is, okay, this one might be a little harder. The probability of 3 or an 8. 3 or an 8. So
for 10?
Here, huh?
I can't see it. For 10, I can't see it. Oh, we're still on D. Oh, we're still on 9.
Yeah, we're still, this is 9D right now, and then we'll get to number 10. And did you do these two already? Did you just need me to check your work, or did you want to go on to number 10?
Let's just keep on number 9.
Okay. So
I only saw like
probability of
3 questions. So
probability of 3 or 8. Okay, how many? Remember when we have or, what do we do?
we add them.
We add. So we're gonna say how many? 3. Okay, so let me do this. Let me go back here. This is gonna be, okay, so here we have the probability of 3 or 8 means we get probability of 3 plus the probability of 8, right? So now, how many ways are there to get a 3? How many 3s in the deck?
Let's go to the deck of spades.
Okay, it doesn't specify. It just says 3s. Just says 3s. You're on D, it doesn't specify. Just says probability of 3
4
or 8. Yeah, there are 4 3s. 3 of clubs, spades, diamonds, and hearts, right? And there are the same for 8. The 8 of clubs, the 8 of spades, the 8 of hearts, 8 of diamonds. So that means we're going to have how many cards altogether?
Okay, is 8 over 52.
Right. Very good. So this is going to be, if we want to write this out, this is going to be this way. I'm going to say probability of 3 or 8 is going to equal 4 out of 52 because they're plus another 4 out of 52. And that's going to give us 8 out of 52, which is going to reduce by 4. So 8 out of 52 here this is going to be, you divide that by 4, you get 2 out of 13. So that is going to be 2 out of 13. When you're done here, this is 2 out of 13. 2 out of 13. Okay, now the next one might throw you off a bit. So let's see how we do there. The next one says, find the probability of a 6 or a spade. A 6 or a spade. So here.
Oh, that means we have to add more?
Well, we're adding more cards, but something else happens. That hasn't happened yet. We're going to talk more about this in 4.2, but that's why you only have one of these, just to show you. So 6s, how many, let's do what we normally do. How many 6s do we have?
We have 4.
That's not a problem. That's easy, right? So there are 4 6s here.
So 4 out of 56.
Spades are my second line right here, right?
Yep, which is 13.
Those are 13, but we've got a problem. Did you notice anything? I counted the 6s here, here, right? And then I counted the spades here.
Yeah, but the 6 of spades counts.
Yeah.
As one number.
The thing is, do I want to count this twice? I don't.
So 3 over 52.
Interesting approach. You don't divide. Okay, let's think about it like this. If I just counted the cards that fit, right? I would count 1, 2, 3, 4, right?
Mm-hmm.
And then I would have to go 5, 6, 7, 8, 9, but I don't want to count this one again. 10, 11, 12, 13, 14, 15, 16. So here, what happens is I count 4 of these for the 6s. I count 13 for the spades. And then that's 17, isn't it? 4 plus 13. And then how many cards did I count twice? 1. So I take 1 off.
So 16.
So 16 out of 52. Okay. That's how, and we're going to talk more about that in 4.2, what we have when we have overlapping events. Because that's a big deal. Overlapping events are a big deal. So here, we're going to say that this is going to be probability of 6 or spade is going to be the probability of 6, probability of 6 plus the probability of spade. Sure, I turn my caps lock off. Minus, we would write this as the probability of 6 and, because we use and for overlap, but we'll talk, like I said, more about that in the next section. So this is going to be equal to probability of 6 or spade is equal to, this is 4 out of 52 plus 13 out of 52 minus 1 out of 52. And that comes out to 16 out of 52, and then we do a little bit of math. We can divide this by 4. This becomes 4 out of 13. Okay. Good job.
Mm-hmm.
You understood that really well, I think.
Yes, I did.
All right, let's see what else they're giving us here. Now I think it's time for number 10. And so we have a picture of, does your copy have a picture of the wheel? The wheel,
Let me check.
your number 10? It should, but I know an early version went out that didn't have it. So make sure yours has the wheel on it.
Yes, I have a wheel.
Good job. Okay, that's good. A shopping mall has set up a promotion as follows. With any mall purchase of $50 or more, the customer gets to spin the wheel shown here. If a number 1 comes up, the customer wins $10. If the number 2 comes up, they win $5. And if the number 3 or 4 comes up, they win a discount coupon. All right, so the first thing we have to do is count how many sections does the wheel have? How many sections?
1. 20.
It has 20 sections, right? Now, what does it take for the person to win $10?
1.
They have to get a 1, right? So how many 1s are there?
2.
Yes. So now, what is the probability that they're going to win $10?
1 out of 20.
Close.
Oh,
close.
50%.
Probability of, you were almost there. So the probability that they win $10, right, means that this is equal to the probability of seeing a 1, right? And how many number 1s are on the wheel?
2.
There are 2 on the wheel out of 20, right? Be careful. That's a common mistake. Be careful not to assign the number to the number of ways it is in the sample space. There are 2 number 1s here. So this is 2 out of 20 reduces to 1 out of 10. And that's 10%. Okay. Good job. 10%. So here, what about letter B? The customer wins money of some sort. So he's going to win money if the number 1 comes up or the number
5.
2. The number is a 2. If a number 1 comes up, right, he wins. Okay, he wins $5 if the number 2 comes up. So we know there are 2 number 1s. How many number 2s are there? 1.
Also 2. There's 2 of each.
There are 2. Oh, okay. Well, I see more 3s. But yeah, there are 2 of each of those. So this is going to be the probability that he wins money is going to be equal to 4 out of 20, right? Because as you said, there are 2 of those. There's 2 number 1s and there's 2 number 2s, right? And that reduces to what? 1/5, which is 0.2. 0.2.
Wait, 1/5? Don't you mean 1/10?
It's 4 out of 20, isn't it?
Yes.
4 into itself goes 1, and 4 into 20 goes. The first question that they win $10 is 1/10.
Oh.
The second question that they win money is 4 out of 20 or 1/5.
So it equals 20?
20%, right? So they have a 20% chance of winning some money, right? All right, now how about winning a coupon? They win a coupon if they get 3 or 4 to come up.
Winning a coupon. Okay, so there's one, either 3 or 4.
3 or 4.
So 1, 2, 3, 4, 5, 6, 7, 8. 8 for 3. So we add 52, and then 1, 2, 3, 4, 5, 6, 7, 8. It's also the same.
Right. But it's not out of 52. It's out of how many?
20. Sorry.
20.
I got
No, that's okay. So how many altogether?
16 over 20.
6. There you go. So the probability that they win a coupon, right, is equal to the probability of rolling a 3 or spinning a 3 or spinning a 4, right? And so that was 16 out of 20, right? And that's 80%. This is 0.8. I think, yeah, 0.8. So then
80%.
That's 80%, right? Okay, that wasn't so bad. There we are, 80%, right? Let's take a look at number 11. Is it okay if I get rid of the comments on the screen? Okay, all right, so there's that. Let's continue. Oops. So we have, okay, come on, scroll. My scroll doesn't want to work right now, which I'm not sure why, but it's asking us about, there we go. It's asking us about blood type, right? All right, so here, human blood, I should be sharing the screen, give me a moment. Human blood is divided into 4 types, and they've grouped it for you in the little chart. So 43% of people have type O, 40% of people have type A, 12% have B, and 5% have AB. Choose one American at random. Find the probability that this person has type O blood. What does the chart say? How many people have type O blood?
43%.
43%. So yeah, this is just about knowing how to read the chart, basically. You have type O blood here. So this is going to be 43%. And I'm not sure why it's acting that way, but let me see if I can make it cooperate here. Okay, there we go. I think that's, maybe not. All right, so this is 43%, just like the chart says. All right. Now, has type A or B blood?
Type A or B blood.
Mm-hmm.
What?
How many people have type A blood?
40.
How many people have type B?
12.
Right. Don't confuse that with AB. Okay. AB means they have both at the same time. Okay. AB is different than either one of these two. So in this case, you're just looking at the probability of type A plus the probability of type B.
Okay.
That is always a little confusing for students when we do that. AB is a type of its own, so she would have had to tell you, okay? So this is just going to be the 40% with type A blood. So this is 40% here. And then you have B is 12%. So that's going to give us 52 altogether, 52%. Okay. Now C, be careful of the way it's worded. Okay. Tell me what you think for C.
Does not have types O or A. 17%.
So, right, because I would be using B and AB in this case, right? So here I'm going to use the probability of B and AB. Very good. Nice work. So this is 5 plus 12. Let me put me be a little more precise. Okay. 5% plus 12%. So this is 17%, as you said. Good job. And that's all we do there is put that in there and continue on. Now this question, it's not meant to be hard, but every semester somebody gets thrown off by one of the parts. So we'll see what happens here. A prime number, this is 12. A prime number is a number that is evenly divisible by only one and itself. Prime numbers less than 100 are shown below, 2, 3, 5, and so on. Here's my numbers, okay? Choose one of these numbers at random, okay? Now notice they didn't tell you how many numbers there are, so you'll have to count it. Find the probability that the number is even. Figure out how many numbers are on there first before you do anything. So I'm going to get my spotlight.
The number is even.
Okay, first of all, they didn't tell you how many numbers they have, right? So we have to count that. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There are 25 prime numbers on this list. Okay. So our sample space has 25 prime numbers, right? So there are 25 numbers on the list. Now, of those numbers that are on the list, the numbers from 2 to 97 here, right? How many of them are even?
Okay, let me see. 1, Just one?
Yeah, just one. So if I want to write the probability that it's even, we go back to the number of ways to have the event. So there's one way, right?
Mm-hmm.
And there's 25 numbers. So my probability is 1 out of 25. Okay. And if I want the decimal, that's 0.04, right?
0.04.
Mm-hmm. And
Also
that
4%.
becomes 4%, right? This is 4%. Good job. Now, how about now? This one is the one that usually messes people up. The sum of the numbers digits is even. The sum of the digits is even. Here you have to, this takes a little more work. The sum of the digits is even. So 2 is even. So that you count that. I'm going to annotate under here. So 2 is even, right? 3 is odd, so we don't count that. 5 is odd, so we don't count that. 7 is odd. These are only one digit, so we don't count that either. When you get to 11, okay, the number is odd, but the digits mean the individual numbers. So here what they're saying is if I add the digits, 1 plus 1, I get 2, don't I?
Yeah.
And that's even. So if I add the digits and I get an even number, I count it. So this counts for letter B, okay? How about 1 plus 3? Is that even?
No.
1 plus 3 is?
Oh, 1 plus 3 is 4.
Right. Don't confuse an odd number with the sum of the digits. Okay, this sum is even. You see that?
Mm-hmm.
What is the sum of these digits?
8.
And that's even, so that would count. How about here?
10.
So we count it.
Mm-hmm.
If we go to 23, what's the sum of those digits?
24.
No, the sum of the digits is?
23.
The sum.
Oh, 25.
Here's 23, right? The sum is 5. So we don't count this one because that's an odd sum, okay? How about here? What is the sum here?
10. Oh, wait, no.
No.
11.
11, so we don't count it. How about here? 31?
4.
Yeah, we count it. How about 37? What's the sum?
10.
There you go. The sum of 4 plus 1?
That's 5. So
We
no.
don't count it. How about the next line, 43?
That's 7.
4 plus 7?
11.
5 plus 3?
8. So it's even.
We count that. How about 5 plus 9?
14 is even.
We count it. How about 61?
That equals 7.
6 plus 7?
That equals 13.
7 plus 1, we count, right?
Yep.
7 plus 3, we count.
Yep.
7 plus 9.
We count. It equals 16.
We count this one. 83, 8 plus 3.
No, it equals
Nope.
11.
8 plus 9.
It equals 17, so no.
And 9 plus 7.
9 plus 7 equals
16. Very good. So now let's go back and count the ones that I circled. So we have 2, that's 1, 2, 3, 4, 5, 6, 7 on the first line, then 8, 9, 10, 11, 12, 13 I got altogether. That's the same thing you have?
Yep.
So the sum of the numbers digits, there are 13 of them that were even, and 25 altogether. So go ahead and we can't reduce this fraction, but we do get a percentage for it, and that comes out to
52%.
52%. So 52% is our percentage. We can write this as 0.52 if we want the decimal. Okay, good job. All right, now here, I'm going to just get rid of the purple. Oops. I said that and then all right, let me, hold on. So let's get rid of the purple so we can do the next one, which is the numbers greater than 50 on the list. How many numbers on the list are greater than 50?
Okay, so 50, starting with 53.
Right here, right? 1, 2, 3, 5, 6, 7,
10.
8, 9, 10. Yep, 10. That was easier to count, wasn't it? 10 out of
25.
25. So what is our, what was that?
Can we reduce it or?
You can, by 5.
2/5.
Okay. Then you make it a decimal number, which
0.4%.
would be,
0.
okay, right now, no, you were right the first time. So it's 0.4. Okay, it's not a percent right now, but if I move it over twice, it will be. Right, so 0.4 is 40%, right? Good job. 40%. All right, now this one, also another sticky one that has some implications for later sections. A couple has 3 children. 3 children. Find each probability. Okay. Now we have different ways of doing this, but in 4.1, we don't introduce a tree diagram in 4.1 usually, but we could write this out. So let me help you with this. What do you think about this one? Finding the probability of all this is, I just want to see if I don't think she gave you the tree diagram for this. I'm just going to check. I don't think we get into that until 4.2. No, we don't. We have that. We have the complement of the event. We have, oh, we do have it. We have it on number 11. We have a tree diagram. So let me show you what that looks like. A tree diagram is a device used to list all the possibilities of a sequence of events in a systematic way. So let me show you this because I thought this was in 4.2, but I was mistaken. So there's a couple of ways to think about this, but if she asks you for a tree diagram, okay, this is a good way for me to show you this. This is let me show you this, and then I have to wrap up, I think, after this one. So here, let me go and say, if you're going to draw a tree diagram, and we're going to draw a tree diagram for 3 children, okay? Draw a tree diagram to represent 3 children. So what we're going to do is we're going to start, I usually do mine from left to right. Some people do theirs from top to bottom. If you're going to do a tree diagram, I suggest you start at least a couple of inches down from the top of your paper, because it's going to expand on you as you go. So you start with a branch that's equivalent to however many outcomes you have. In this case, we have 2, a boy and a girl. So what I'm going to do is I'm going to put first child here next to this branch. And I'm going to label, you can use letters, you don't have to write the whole word, but you should specify what you're using. I'm going to use B for boy and G for girl. And I always have to state every semester, this book was written before the whole gender fluidity issue. So everything in here with genders is binary, but we recognize that genders may not be so, but they're treated as binary in the book. So you should know that. This is the second child here. This is our second child. Now, what's happening here is we didn't all of a sudden sprout 4 children. What we did do was sprout 4 possibilities for how our family could look. That's what this is saying, okay? So we have boy, girl here. And then we have boy, girl here. So this is boy, girl like this, okay? So here means we had a boy and a boy, and then a girl and a boy, or a girl and a girl. We need to have one more child because there needs to be 3 children. So I'm going to put third child up here. And I'm going to specify that there's off of this boy now, I'm going to say that I have 2 off of each, and we'll see if I left enough room, just barely. Well, whoops. We'll make this work as much as we can. Let me undo the last branch that I made, something like this. And then I'll write the branches out. Something like this, okay? Not as great as it could be, but it will do. This is a boy, and this is a girl. And this is a boy, and this is a girl. So here you got girls, here you've got boys, here you've got girls, here you've got boys, here you've got girls. So now, here's what our outcomes are. We have a total of 8, believe it or not. So our family situation is as follows. We could have boy, 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 which is what this top group represents. We could have the next one, which is boy, boy, girl. Which is this next piece. We could have boy, girl, boy. boy, girl, boy. Or we could have boy, girl, girl. Okay. We can also have girl, boy, boy. Or girl, boy, girl. Girl, boy, girl. We could have girl, girl, boy. Girl, girl, boy. Or girl, girl, girl. Girl, girl, girl. Okay. There are a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. All of these outcomes, we're assuming that they're all equally likely. So we're taking some liabilities, we're taking some assumptions here, but we're assuming for the sake of example that they're all equally likely. Okay. And so what is the likelihood? Let's go back to our question so we can wrap this up here. What is the probability that we have all boys? Well, how many outcomes are all boys? Let's go look.
11.
How did you get 11 outcomes?
I counted all the boys.
Interesting. Okay. All right. Remember that the family, that's, wow. Okay. But our family has 3 children in it. So if you count the individual boys, yes, there are 8 individual boys. Okay. But the outcomes are these: boy, 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 girl, boy, girl, because the family has 3 children, not individually. So here, there are 8 outcomes. There are 8 outcomes. Now, how many of them are all boys? Well, the only outcomes that are all boys are the one at the top. The only outcome that's all boys is here, which is, so we would say the probability of all boys is 1 out of 8. Yeah.
Mm-hmm.
Now, how about the probability of all boys or all girls? What do we have to do here?
We have to look. 1. Oh, wait, no.
Yeah. Well, here's one with all boys. Is there anything with all girls?
Yes.
Where is it?
At the bottom.
Yeah. So how many outcomes are all boys or all girls?
2.
2 out of
8.
8, right? Or 1 out of 4, right? 2 out of 8, which is 1 out of 4, right? Good deal. Now, the next thing might be a little bit, might throw you off a bit. Let's see what the next one says. The next part says the probability of exactly 2 boys or 2 girls. 2 boys or 2 girls. So here, let's look back at our chart. Oops. 2 boys or 2 girls. Now, we don't want 3 boys or 3 girls.
Mm-mm.
We want 2 boys or 2 girls. So I'm gonna take off some of these. Which outcomes are we talking about here?
Ones with 2 girls and 2 boys.
Okay, be careful, because we only have 3 children. You choose the ones that have either 2 boys and a girl, like this. Here's another one with 2 boys and a girl, right? Or you choose the ones with 2 girls and 1 boy in it. So you also choose this one. This one, because it has 2 boys and a girl. Here, this one has 2 girls, right? Obviously, you can't have, you don't say and, because then you would need 4 children, wouldn't you? If you had 2 boys, and if somebody came up to you and you asked them, how many children do you have? And they said, I have 2 boys and 2 girls, that's 4 children, right? 2 boys or 2 girls. This is tricky, okay? So this includes all of the outcomes except for the one that you just created. So if I said the probability of 2 boys or 2 girls, that's in any order, in any placement. This is 6 out of 8, which is 3 out of 4, or 0.75. Okay, now the last question says, let's do this. The last question here says at least 1 child of each gender, at least 1 of each. At least 1 of each. So here, if you have at least 1 boy and 1 girl, you want 1 of each. You could have 2, but you don't want all 3 to be the same. Okay. So here, you're going to count the same 8 that you counted before, but for different reasons, okay? This second group has 1 boy, 1 girl with an extra boy. This has 1 boy, 1 girl with an extra boy. This has 1 boy, 1 girl with an extra girl. This has 1 girl, 1 boy, an extra boy on the end. This has 1 girl, 1 boy with an extra girl on the end. This has 1 girl, actually has 2 girls, but you have a boy at the end, so that would still work. The only ones we don't want are the ones that are all boys or all girls. So that's the same thing as the previous one, but for different reasons. So this is the probability of at least 1 of each. And that's the same probability with the same mathematics of it, but for different considerations. Okay, we're going to be coming back to a problem like this and talking about probabilities and how probabilities work together, but not in this section. In 4.2 and in 4.3, we're going to talk more about it. But I have to stop here for now. Okay, but I hope that gives you a good start.
Yes, it did. Thank you.
I think you're off to a really good start. Congratulations on that. Okay.
Mm-hmm.
We'll see you again soon. Okay.
Okay. Bye.
Take care. Bye now.